A very good morning to all of you, and in this lecture, I'll be talking about. I'll actually go with uh, the hermitian, with the property of hermitian. I mean, uh, we have we deal with hermitian operators in the previous lecture, and we defined what a hermitian operator is. In this, so today I would like to extend, I would like to move on with some more properties of hermitian operators. And to start with, if we have two wave functions, psi1 and psi2, and we have an operator, say x cap, and if this operator acts on psi1, I get, say, lambda 1 psi1. And if I operate the same operator on psi2, I obtain lambda 2 psi2. So what is presumed here is that that the wave function psi1 and psi2, these are normalized wave functions. Normalized wave functions. So using this data and using the property of using the Hermitian property of these operators, assuming that this operator is a Hermitian operator, we would like to prove the orthogonality condition. I mean to say, I would like to prove that the integral minus infinity to infinity psi1 star psi2 d tau is equal to 0. So this should be our target. So using the Hermitian property, using the property that the operator that we have been using here is a Hermitian operator, we would like to prove that psi1 and psi2, they are orthogonal to each other. So this is our target. Our target is to prove that the wave function psi1 and psi2, these two wave functions, which are basically normalized wave functions, these two wave functions are orthogonal to each other. And we can see that when we operate on psi1, we get energy eigenvalues as lambda 1, and for psi2 we get the eigenvalues as lambda 2. So putting down lambda 1 and lambda 2 is an indicator of the fact that lambda 1 is not equal to lambda 2. So we'd like to proceed for the proof of this orthogonality condition. So we will start with the property. So when an operator is Hermitian operator, then there is this equation is satisfied. Minus infinity to infinity psi1 star x cap psi2 d tau is equal to integral minus infinity to infinity x cap star psi1 star psi2 d tau. So we understand that this operator can be Hermitian operator only if this condition is satisfied, right? So we can think of what we have is we have x on psi1 giving us lambda 1 psi1, and x cap, if I take the complex conjugate, x cap psi1 star will be equal to lambda 1 star psi1 star. And same thing will be true for x cap psi2 giving us lambda 2 and psi2. So taking its complex conjugate, what we will have is x cap star psi 2 star is equal to lambda 2 star psi 2 star. So clearly we can use in the left hand side for x cap psi 2. So x cap psi 2 will give us lambda 2 psi 2. So I can use this part here in the left hand side of the equation, and x star cap psi 1 star, x star cap psi 1 star is equal to lambda 1 star psi 1 star, and I can use this condition in the right hand side of this equation. So actually, what's the motivation is that I have to obtain mathematically the orthogonality condition. When we have two wave functions and the operator that's operating on the wave function is a Hermitian operator. So what's going to happen is, okay, so I'll have integral minus infinity to infinity, okay, yeah, psi 1 star, and then psi 1 star, okay, then x cap psi 2, what's that? That is lambda 2 psi 2. So here I will have lambda 2 psi 2, okay, then I'll have d top. Okay, so what will be in the right hand side? Okay, so this will be equal to, this has to be d tau here. So we are taking the volume integral here. So here for x cap star and for x cap star and psi 1 star, x cap star and psi 1 star will give me lambda 1 star and psi 1 star. So this is equal to integral minus infinity to infinity, then lambda 1 star, and then you will have psi 1 star and psi 2 and d top. Right. So I can transform the right hand side and the left hand side. What I'll get integral minus infinity to infinity psi 1 star psi 2 d top times, so lambda 2 minus lambda 1 star is equal to 0. This is what we will obtain. And we know that this lambda 1 star is equal to lambda. This we have already proved that when you execute the Hermitian operators, the eigenvalues that we obtain, they are real. So if they are real, then this lambda 1 star is equal to lambda 1. So instead of lambda 1 star, I'll be writing down here. I'll be writing down here lambda 1. Better is to write another equation. So I'll be writing minus infinity to infinity. Then I have psi 1 star, and then psi 2 d top times lambda 2 minus lambda 1 is equal to 0. Now, what is important here is that the product of the two is equal to 0. So either this has to be equal to 0 or this has to be equal to 0. Now, what we understand is that this lambda 2 is not equal to lambda 1. So if lambda 2 is not equal to lambda 1, this bracketed term has a non-zero value. And if this bracketed value has a non-zero value, then we can automatically say that minus infinity to infinity psi 1 star psi 2 d top is equal to 0. So in this way, what we have done, we have obtained the relation that we were interested in, and what we have obtained is that the two wave functions psi 1 and psi 2, they are orthogonal to each other. So this was one important property of these Hermitian. Using Hermitian property of the operators, what we have done is we have proved that these two wave functions, psi 1 and psi 2, these two eigenstates are orthogonal to each other. Now let's go with another, let's let's prove another important mathematical parameter. And what is that? Now, if I assume that I have two Hermitian operators, I take on two Hermitian operators. And what are these Hermitian operators? Alpha cap and beta cap. So assuming that alpha cap is a Hermitian operator and beta cap is a Hermitian operator. And these two operators commute. So if these two operators commute, assuming that these two operators commute, so what this will be equal to, this is, if they commute, their result is equal to 0. So what is the result of this commutation is alpha cap, beta cap minus beta cap, alpha cap is equal to 0. So alpha cap, beta cap is equal to beta cap, alpha cap. All right? So we are just trying to build a problem first. So I assume that there are two Hermitian operators, and these operators are alpha cap and beta cap. And I assume that these two operators commute. So if they commute, their result is equal to 0. So if their result is equal to 0, then I expand this commutation between alpha cap and beta cap, and I can think of alpha cap, beta cap equal to beta cap, alpha cap. Now, the question is that I want to prove now, if these conditions are there involved in my problem, I want to prove that the product of alpha cap and beta cap is also a Hermitian operator. So everything is built in a systematic way. Alpha cap is a Hermitian operator, beta cap is a Hermitian operator. So for alpha cap to be a Hermitian operator, then the wave function that's linked with alpha cap has to be a normalized wave function. And the same thing is true for the beta cap. But what am I trying to do here is that I'm trying to tell you that if alpha cap is a Hermitian operator, beta cap is a Hermitian operator. So I would like to prove that their product, alpha cap, beta cap, is also a Hermitian. So that's my intuition. That's what I want to reveal here. So what's that? So what I want to prove is that alpha cap and beta cap, this product is also Hermitian. And this is what the target is. So if this has to be Hermitian, it should satisfy what? It should satisfy minus infinity to infinity, psi star, then alpha cap, beta cap, and let me use the same psi, dx, if we take it in one dimension, is equal to integral minus infinity to infinity, alpha cap, beta cap, psi star, psi dx. All right, so this is something, if I can prove that this equation is true, then I can say that the product of alpha cap and beta cap is also a Hermitian. So that's our target. So in proving this thing, I would like to choose the left-hand side of this equation. So this is the traditional way of doing these things. So if I obtain the right-hand side by evaluating the left-hand side, then automatically I'll be in a position to declare that the product of these two Hermitian operators is also Hermitian. So what should I do? So I'm taking my left-hand side. So from left-hand side. So what's that? That is integral minus infinity to infinity, psi star, alpha cap, beta cap, then psi, and dx is equal to. Okay, I can think of writing this thing as minus infinity to infinity, then psi star, alpha cap, and beta cap, psi dx. Okay, so I think I should use d tau. Let's use the same d tau here. Okay, so this is d tau, and here I have d tau. Okay, now taking this as an overall function and this as another overall function, I can use the property of Hermitian operators because I know that alpha cap is a Hermitian operator. I know that beta cap is a Hermitian operator. So if I use that, what I'll be writing here is, I'll be writing here using the property of Hermitian operators. This will be minus infinity to infinity, and then I have psi star, but that beta will come here. So beta cap will be here. So inside I'll have alpha cap and psi and d tau. That should be the case. Now again we can see that that we have alpha cap. This alpha cap is a Hermitian operator, so it should also take on the property of Hermitian operators. So I should be writing for alpha cap as minus infinity to infinity. Beta cap is first, then alpha cap will come here. So inside I'll be using psi star, psi, and d tau. Now, if you rightly go back to the commutation relation, because what we assume in this problem is that alpha and beta, they commute. So if they commute, then alpha cap, beta cap is equal to beta cap, alpha cap. So, so instead of using beta cap, alpha cap, I know that alpha cap, beta cap is equal to beta cap, alpha cap. So if that's the case, then I can write this as minus infinity to infinity, alpha cap, beta cap, psi star, psi, and d tau. So we can observe the result. So this way what we have done is we have proved that, that if we have two Hermitian operators, alpha cap and beta cap, if you take the product of these two Hermitian operators, their product is also Hermitian. So the result is obtained here. So the result is what? The result is I have two operators, psi star, then alpha cap, beta cap, and then psi d tau. This is equal to integral minus infinity to infinity, alpha cap, beta cap, psi star, psi, and d tau. So this equation proves mathematically that these two operators, which are independently Hermitian operators, if you take the product of these two Hermitian operators, their product is also a Hermitian operator. Now let me go with another important example of Hermitian operators. And what's that? That is, let's go with the momentum operator. So let us prove now that momentum operator is a Hermitian operator. Let's do it. Is a Hermitian operator. Now we know that momentum is a vector quantity, and if momentum is a vector quantity, it has components. So it has components like px, it has components like py and pz. So we can take on px. Okay, if I prove that px is a Hermitian operator, then automatically you can prove that py and pz are also Hermitian operators, and you can generalize the situation that this momentum operator is a Hermitian operator. So that should be our target. And let us start with this. What is px? Px is minus ih bar dou by dou x. This is the momentum operator, the x component of this momentum operator. So for this operator to be a Hermitian operator, what is required? If I take on two functions, if I take on psi star, then p cap, then psi, and then let's take it in one dimension because this is chosen from one dimension as dx minus infinity to infinity. This must be equal to integral minus infinity to infinity. Then psi, no, then p cap should be out. Px, it has to be px. So px cap is out, and inside we have psi star, psi, and dx. So this equation we have to prove. If we are able to prove that the left-hand side of this equation is equal to the right-hand side of this equation, then automatically we can say that the momentum operator is a Hermitian operator. So for the momentum operator to be the Hermitian operator, this is the necessary condition to be proved. So what should be done in the traditional way? I will take the left-hand side. Okay. So if I take the left-hand side and if I obtain the right-hand side, here it has to be the star. Okay, I might have committed this thing. Okay, it has to be the star. Maybe, yeah. Here it had to come up with star. You can check it out. It will come up as stars. Okay, so because alpha cap and beta cap as equivalent as that of beta star and alpha star. So you can do that. I don't know. I have missed it a little bit. You can perceive it yourself. So here in this problem, I will choose the left-hand side. So if I choose the left-hand side, what is the left-hand side? It's minus infinity to infinity. Then you have psi star p of x psi dx. So this I can write as minus infinity to infinity. Then psi star, for px I have minus ih bar d by dx of psi, and then you have dx. So if you rightly remember in the previous lecture, I said that psi has to be normalized. Now if psi is normalized, what does that mean? That means minus infinity to infinity psi star psi dx must be equal to 1. And what it means, in other words, is that if this x tends to plus infinity, then the psi will be equal to 0. And if this x tends to minus infinity, this psi or psi star should be equal to 0. So this is the important condition that we already know, that we have already discussed, that we have already talked about. So now what we have here, I think I will get minus ih bar out. Okay, integral minus infinity to infinity. Then I will have psi star. Then I will have dou psi by dou x, and then I will have dx. So it has to be dou and dou. Okay, right. Now what I have, this is my u and this thing is my v. So I have integration of u and v here, and let me exploit this integration. So when I exploit this integration, minus ih bar will be outside, and inside I will have u as x, so psi star as x, into the integration of v. So what is v? This is integration of dou psi by dou x, and then dx. Okay, then I'll have minus integration of, so your limits are from minus infinity to infinity, minus infinity to infinity. Then here what I will have is differentiation of u, so that will give me dou psi star by dou x. Okay, and the integration of the v. What is the integration of v? Integration of v is dou psi by dou x, and then I will have dx. Okay, and here we can see this is minus ih bar, and here I will have simply psi star, and here I'll get psi, and it will range from minus infinity to infinity because the integral and differential can be removed, and then I will have minus integral minus infinity to infinity then dou psi star by dou x, and here integral and differential will be taken off, so you will have psi dx here. So I will close the long brackets. Now look at the first term of this thing that's on the board. I have psi star and psi. And as I told you before, as x tends to plus minus infinity, the value of psi and psi star has to be equal to 0. So this term will automatically be equal to 0. So what we'll be left with is minus IH bar, and I will multiply this minus IH bar with this minus, so it will become plus IH bar times this term. So what I will obtain? I will obtain IH bar integral minus infinity to infinity, then you have dou psi star by dou x, and then you have psi, and then you have dx. This is it. All right. So I can take this IH bar inside. This is minus infinity to infinity. So I can write down IH bar dou by dou x. And then psi star I can write outside, then I have psi, then I have dx. Right? And you can see here, this is IH bar dou by dou x. What is this IH bar dou by dou x? See, if I talk about px, px is minus IH bar dou by dou x. Then what is this plus IH bar dou by dou x? It is basically the complex conjugate of px. So if px is minus IH bar dou by dou x, then px star has to be plus IH bar dou by dou x. You can put a star here, no problem. So what's going to happen? So this is my px star. So this is my integral minus infinity to infinity px cap star, then psi star psi dx. Maybe I don't remember exactly, I might have committed a mistake somewhere in terms of the star, then I request you that you can fix that yourself. So you can see the result that I have obtained here. This result is exactly the same thing. And what is this result? This result is like this, that you have an integral minus infinity to infinity, then you have psi star, then you have px cap, then you have psi dx. We have proved that this thing is equal to minus infinity to infinity, then, okay, we have proved this is equal to px cap star psi d top. So this equation is true. So if this equation is true, then I can say that this px cap is a Hermitian operator. So momentum operator along x is Hermitian operator, and you can take the similar considerations for y and z, and you can generalize this result that the momentum operator in quantum mechanics is basically a Hermitian operator. So with this, I would like to stop this discussion, and if you have any questions, you can ask me, and you can later on communicate with me, and I hope you got the point.